And this is the math final project. And let's get this set up. Perfect. So the first problem I chose to do, number one of the optimization problems. The problem is I have to build a rectangular pen that contains 3 partial sections. So let's draw that out real quick. Here's our pen. Call this Y, this X. Here's another X, and then 3 sections. 1, 2, 3. And these are all fencing, so I'm going to label all of them as X, since the fencing costs money. And we only have 500 feet of fencing. So 500. Now that 500 is going to be equal to, since you have 2 y's, it's going to be equal to the equation 5x plus, it's going to be equal to the equation 5x plus 2y. Now, we're going to solve for y. So let's make this 2y is equal to 500 minus 5x. Perfect. And simplify by 2 and make this y equals 250 minus 5 2x. Now, the next thing we're going to do is make an equation for the area. Right. So our equation for the area is going to be A equals x times y. Simple as that. So A is going to be equal to x. Then we're going to substitute in for what we got for y, which is right here. X times 250 minus 5 over 2 x. And we'll throw that in parentheses so there's no confusion. And then we're going to, what is that called? I'm going to spread this x across the equation, whatever that's called. A equals 250x minus 5 over 2x squared. Perfect. Now we're going to find the derivative of this. So derivative of area is equal to 2. So we bring the x back here. 1 times 250 is 250. Take minus 1 off that. So it's going to be 250. Oh, oopsies. So 250 minus, times this by 2, equals 5 minus 5x. Take minus 1 up here, so that becomes a 1, x is first, just x. And then we have our derivative. Now we're going to make this equal 0. So 250 minus 5x equals 0. So it's just going to be 5x equals 250. We're going to take out a 5, and that's going to become x equals 50. Now we have our x. It's that easy. So now we're going to plug this back in and find our y. So if we plug it back into 2y equals 500 minus, it's going to be 5 times x, and 5 times 50 is going to be 250. So 2y is going to be equal to 250. Oops. 250, and y will be equal to 125. So now we have both our y and our x. So we'll multiply those together to get the maximum area of 6,250. And that's with 500 feet of fencing. Our maximum area is going to be 6,250. And put a little number line. Here's 50. Anything above 50 is going to be negative, and it's going to be positive. And it's going to be x equals 50, y equals 125, area equals 6,250. And if x equals 100, then y and area both equal 0. And the same thing down here. If x equals 0, y equals 100. Area, or I'm sorry, y equals 250. There's going to be equal to 0 as well. So, this is our maximum. Now, the second problem, I'll do that. So, the camera angle is not that good, but I'll be sure to display everything after I'm done with both the problems. And so for the next problem, I chose number, let's see what number it is. It is number 2, so I chose number 2. And the question is asking me to find the radius and height of the most economical can. So I'm trying to find a can that can hold an area of 20 pi meters cubed. So I'm trying to find a can that can hold that for the cheapest. And the cost, let's see, so we have the top of the can, here's the bottom of the can, and the top and bottom both cost $10. $10 per meter squared. So cost equals meter squared per meter squared. So let's see the material for the side. Cost $8 per meter squared. Remember that? And then so we have to find the radius and the height. So the radius is going to be half the base. It's going to be r, and the height is obviously going to be the height of the can. And what I'm going to start off going to do is going to find an equation for the height, I guess. So height equals, let's see, I did these problems out beforehand, and I'm just going to check this as a reference. So, okay, so the height is equal to 20 pi over pi r squared. And our equation for the area is going to be 20 pi equal to pi r squared times h. So the area is going to be 20 pi. This is our equation for the height, or for the radius. And we're finding h right now. So since this is 20 pi over pi r squared, I'm just going to take away the pi, and that's going to make height equal to 20 over r squared. And now that we have our equations for h and area, we're going to plug it in so we can find r. So this is going to be a cost function. So we can find the best price, and the cost is going to be equal to the top, which is going to be 10, and the equation for the top is going to be pi r squared. And then we also have to find it for the bottom, so plus 10, again, pi r squared. And then we're going to have to find it for the side. And the equation for the side is going to be $8. And the equation to find the side is going to be 2 pi r height. So $10 times pi radius squared plus another $10 times pi radius squared plus the side is going to be $8 times 2 pi radius times height. Now, we can simplify this. You can just put these together, so we get 20 times pi r squared plus, we can just move this 2 on the outside, make it 16, and then times pi r times height. And then, now what we're going to do, we're going to get rid of these parentheses. C equals 20 pi r squared plus 16 pi r, and then we're going to plug in what we found for h, which was 20 over r squared. So now we've eliminated a variable, and we're going to solve this for r. And to do that, we're going to have to find the derivative. So, well, actually, first we're going to combine this. So we're going to make it c, we're going to clean it up a little bit, make it look good. 20 pi r squared plus 320 pi r over r squared. And then we're going to get rid of that, so it's just 320 pi over r. Great. So now we're going to move on to the derivative, so we can find the best cost, the most economical. So the derivative, 20 pi r squared, is going to be 40 pi r plus the derivative of 320 pi over r. So to find the derivative of 320 pi over r, we're going to make it, let's work this out over here. So first, we're going to take 320 pi, and then we have to multiply it by 1 over r. And then we're just going to add this little n so we know what we're doing at the top. So now to make this something we can find the derivative of, since it's a fraction, we can make it 320 pi times r to the negative 1. So since it's a fraction, you can bring this down here and make it a negative and get rid of it. So now we have 320 pi times r to the negative 1. And to find the derivative of this, we're just going to take this negative 1, multiply it by that. So we have negative 320 pi r to the negative squared. And then we're going to bring that down here, but we'll write it over in the equation. So the derivative for the cost function is 40 pi r plus negative 320 pi over, I'm going to bring this r squared down, make it a positive, over r squared. So that's our derivative. And we're going to change that up a little bit, take away the positive, make it just negative. Cool. Now, what we're going to do next is make this a common, we're going to make them a common denominator. We're going to combine the like fractions. So what we have to do here is multiply both sides by r squared. So it's going to be 40 pi r cubed. Hold on. 40 pi r cubed. Let's see, right here. 40 pi r cubed minus 320 pi over, and then we're going to move this r squared back down to the bottom. R squared. And this looks really messy up in here. The numerator is really messy, so we're going to clean it up, and we're going to take the 40 out of it. So we're going to end up with 40 40 pi. We're going to take the pi out also as well. 40 pi, and then it's going to leave us with r cubed minus 8. R cubed minus 8 over the r squared. And this won't matter because all we have to do is find, we have to make the numerator equal 0. 40 pi r cubed minus 8 equal to 0. And then just move the 8. We can just move the 8 over here, and we're going to have r cubed equal to 8. R will be equal to, what is that, 2? 2 things, yes. R is going to be equal to 2. And now, if we plug this back into our height function, we get height, which is equal to 8. And we also get our cost. When we plug this into the cost function, which I did beforehand, we're going to get a cost over here. I'll show you my initial work after, but we're going to get a cost of 2, what is it going to be? 1 second. 240 pi. And then multiplied by pi, cost is going to be $754. That is the cheapest amount to get a can with an area of 20 pi meters squared. Now, so those are my first 2 problems of choice. And for a closer look, here is all the work I just did. Here's all that. So you can check it, make sure it's all plays out, which I'm pretty sure it does. And I did this beforehand so I wouldn't mess up on camera, which I may have done anyways, but here is all the work I did beforehand, which might have a little bit more detail in it. All like the math and plugins were in here. And then now I'm going to move on to the problem. The last problem, the function. So, let's see. Okay, so the function that we were given is going to be s of t, and s of t is location. Let's see. So our position is going to be equal to, let's see, t cubed minus 6t squared plus 9t plus 1. So that is the equation we were given, and that gives us our position. So now we got to find the velocity. And the velocity is just the derivative of s of t. So v of t is going to be 3t minus 12t plus 9, and that's going to be it. So now what we're going to have to do is find where the velocity stops. So to finish the graph as the final product, we're going to need to know when it stops and changes directions. So what we're going to need to do is simplify this. And this one's quite easy because we can just divide it by 3. And then we get t minus 4. Oh, I'm sorry. That's not right. That's not right at all. Okay, we're going to get t squared minus 4t plus 3. And we can factor out that negative 3 plus negative 1 equals negative 4, and negative 3 times negative 1 equals 3. So this is going to be super easy because we can just do t minus 3 times t minus 1. So that means our t's are equal to 3 and 1. So now we have our stops. Great. Well, so 3 and 1. So when I plug 0 into the initial equation for v of t, it's going to be positive. And when I plug 2 in the equation, it's going to be negative. And I believe it's going to be positive again. Yep. Plug 5 in, it's going to be positive again. So here is our directional movement. And yeah, we have our direction of movement, right or left. So it's going to go right, then left. So it's going to go right, stop at t equals 1, move left until t equals 3, and then move right. So then we have that part of the graph. So we're also, for the final product, we're going to need to find our initial starting point, or what's it called? Our initial the initial position is what we're going to call it. So to find the initial position, we call it IP equals S of 0. And if we plug 0 in here, 0, 0, 0 plus 1, we get 1. So our initial position is going to be 1. Now we have to find the acceleration. Oh, and if this should be labeled, this was A. This is part A of the problem. So now part B is finding the acceleration, A of t. And the acceleration is the derivative of the velocity. So we're just going to find basically the second derivative of the position, S of t. So it's going to be, oh, this should be squared. Whoopsies. So velocity, I made a mistake, it's going to be 3t squared minus 12t plus 9. Okay, so now the acceleration is going to be 6t minus 12. That's simple. And then we're going to make it equal 0. So 6t minus 12 equals 0, which is going to be 6t equals 12. And then divided 6, and we have t equals 2. Throw this in the number line, and we get 0 equals negative, put in a 3, and we have positive. And now we know where the acceleration is positive and where it's negative. So to make this easier for our final graph, we're going to put these two together. Sorry, but sitting kind of awkwardly. Okay, so what we're going to do now, we're going to make our velocity chart. We're going to make our acceleration chart. And we're going to make them so they're equal. And then we're going to have boom, 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 boom. Okay, so V of t, A of t. This is going to be 1. This is going to be 2. And this is going to be 3. So from the velocity, 0 to 1, or negative infinity to 1 is positive. 1, 2, 3 is negative. And 3 to infinity is positive. And then, or not, 3 to infinity, I'm not quite sure what it is afterwards, but we're going to have to find, the problem is asking us to find from t equals 0 to t equals 5. So from 0 to 1, it's positive. From 1 to 3, it's negative. And from 3 to 5, it's positive. And then for the acceleration, from 0 to 2, or I guess the initial position is 1, but that doesn't matter right now. So from 0 to 2, it's going to be negative. From 2 to 5, it's going to be positive. And now we know. Now we know when it's speeding up and when it's slowing down. So right here, it's slowing down because they have different signs. Right here, it's speeding up, slowing down different sides, it's speeding up the same signs. So now we have most of our problem, and all that's left is just solving for the points of t and putting together the graph. So I did the liberty of going ahead of time on my calculator and plugging in all what t equal when plugging it back into the position, so we wouldn't have to go through the time of me solving it. So what I did was I plug into my calculator. For t, I'd enter 3, so it'd be 3 cubed minus 6 times 3 squared plus 9 times 6 plus 1. Or 9 times 3, I'm sorry. So I'd plug in 3 for all these t's and solve it. And for s of 3, I got 1. For s of 1, I got 5. For s of 0, which is the initial position, which we already got, is going to be 1. And then s of 2 equals 3. S of 4 equals 5. Now I found all these positions, but really the only really important ones are going to be 1 and 3. So we're going to start off with this graph by starting with a line beginning at the initial position, which is 1. So this is going to be a graph with the initial position of 1. 5 is going to be down here. 1. We're going to get 2, 3, 4, 5. Perfect. So now, our first stop is the initial position at t equals 0. T equals 0, it's at 1. And we know at t equals 1, it's at 5. So, and from this we know it's speeding up from t equals 0 to t equals 1. We know it's moving to the right. And now we know at here it's going to transfer, and it's going to go left. And then at s equals 2, it's going to be at 3. So right here, it's going to be at 3, and it's going to start slowing down. It's going to be t equals 2. And then we know at t equals 3, it's going to be back at the initial position. And it's going to stop. And it's going to turn around and start moving right, and it's going to continue moving right, we know, for the rest of the graph. But now we can plug in for 4 and 5. And we know at t equals 4, it equaled 5. Boom. And then it's off the graph. And at t equals 5, which we didn't solve yet. So we can solve right now. Or at t equals 5, it's just off. It doesn't really matter. But yeah. That. So this is going to be the completed problem with the graph. Oops. Okay. So to walk through, we have our position. We have our initial position. We have the velocity, and then we have our t's where it stops, where it comes, and it switches from moving right to moving left, and then moving right again. And we know we have to solve it from 0 to 5. So we find the acceleration, find when it's speeding up, or when it's speeding up and slowing down, and moving up and moving down. So we can apply all that, our initial position, our stopping points, where it's moving left and right, and where it's speeding up and slowing down, to get this graph. And that's going to be all 3 problems.